So this afternoon, I'm going to talk about this work. So we started this a long time ago. Steve and Howard and I had this conversation at some conference at lunch about this paper that Jeff Kling and Larry Katz had written about moving to opportunity, where they had tried to use this instrumental variable strategy to try to estimate the effects of more than one mediator at a time. And we were sort of thinking, does this model really work? What are the assumptions of it, and do we believe it? And so that led us down this long road, which we have been on. So now we know the conditions under which it works. And so that's what I want to talk about today. Basically, the question is, the stuff Steve showed you this morning with the instrumental variables model works when you have one mediator. So you have, and in his case, the mediator was, do you take up the program? Do you enroll in Head Start or a charter school or whatever the program was? So you have randomization, and then the mediator, the only way that the randomization can affect you is if you take up the program. And so you have one instrument per site, you have one mediator per site, you have an exclusion restriction that says if you didn't take up the program, then your random number didn't affect you, right? You're either an always taker or a never taker, so randomization doesn't affect what you do. Only the compliers get affected. So that's great when you just have sort of the one mediator. But what if you think that the treatment might operate through more than one pathway, essentially, so that you can't draw that little picture that Steve showed you where you have treatment, arrow to mediator, arrow to outcome, no other arrows, right? So that's what I'm going to sort of try to talk through today about how to sort of build on this instrumental variables models when you have multiple sites, and how can you leverage those multiple sites to get the effects of multiple mediators. So I'm going to, that's the outline. We have this, there's handouts, right? You guys have do they print them out? They're in the back if you want them. Okay, so while those are getting passed around, here's an example. Suppose we offer families a nice $5,000 voucher to pay for preschool. We randomize you whether or not you get the voucher or not. We want to know whether or not offering people a voucher improves children's school readiness. And so under random assignment, we can estimate the intent to treat effect of getting the voucher offer, and we can know whether or not sort of offering vouchers is an effective way to improve school readiness. And we could also, as Howard showed you yesterday, we could estimate the variance of that treatment effect. If we have a multi-site trial, we can look at the effects of the voucher offer in different sites. But suppose we don't want to just know what the effect of the voucher is, but we want to know why the voucher works. What does it do to people? That's the sort of active ingredient. Obviously, getting them to go to preschool might be one such thing. So I want you to think about this. So we're gonna do some interactive things here. So I've never done this before, so this is a learning experience for me. But if you we're gonna use this little poll everywhere thing. How many people have used this? Okay, so some of you are cooler than me. Some people already put things in. Who did this? How did people see that? So if you go to this website, polev.com, Sean Reardon 222, or I think if you text this thing to that number, you can do it on your phone. It will let you answer this question, and we'll see your answer. So I'm going to give you a minute to do that. Imagine we have some measure of literacy or something at school readiness. So, you know, I don't know, some generic measure of, you know, literacy, numeracy, focus, executive function, whatever you want it to be. So we got preschool quality, parents have more money, parents can work more literacy resources at home. I don't know how to scroll down, so I got to read them as they go, otherwise they're lost to history or something, right? Some. I don't know if there's going to be a word cloud. Yeah, access to peers, parental income.
I think there's a bar on the side.
What does that bar? Oh, it lets me scroll down that bar. Oh, look at that. So, look at that. I can scroll right down. So, all right, good. Attending preschool, that's an interesting mediator. Yeah, that probably helps, right? Parent knowledge of child development, interesting. Stress reduction. All right, I'm going to give you one more minute if anyone has mediators left to suggest. Howard, did you make it work on your phone? Yeah. Structured time, local preschool options. So the idea here is there's a lot of potential mediators that we might hypothesize through which getting the voucher getting the voucher offer might impact school readiness. And so you can imagine some of these are not sort of mutually exclusive, right? Like if you imagine that one pathway is, well, you're more likely to go to preschool if you get the voucher, so that's probably one mediator. But as some people suggested, getting the voucher offer might give parents more knowledge, or it might give parents more money, either because they can work more or they just have money in their pocket, even if they're an always taker, right? Think about this. Suppose you're an always taker. Your kid would go to preschool whether you got the voucher or not. The exclusion restriction says the voucher offer can't affect your outcomes. But if you're an always taker, the voucher offer puts $5,000 in your pocket because you were spending that money to send your kid to preschool anyway. Your kid's still going to preschool. Maybe their preschool experience is identical. But you have $5,000 extra money, and maybe you use that in ways that affect your child's school readiness, right? So under that, a set of mechanisms, the exclusion restriction isn't valid if you sort of think of the only pathway being enrollment in preschool, because now this other pathway can affect the outcomes of always takers, and so you would no longer be able to use the sort of single instrument, single mediator thing, right? So you can sort of see there's multiple ways that you might imagine that this voucher offer might affect children's outcomes, and what we would like is to be able to estimate a model that gave us unbiased estimates of the effects of those different mediators on your school readiness, which we can't do in a simple one site, one instrument IV model because we can only identify the effect of one mediator when we have one instrument. And so the logic of what I'm going to talk about is a method of using multiple sites to get around it. All right, we're going to go back here. Look at that, it works. Okay. What this does not. All right. So here's a simple theory that says there's two mediators. You get a voucher offer, and that might affect how much time you spend in preschool, but it also might affect the amount of academic instruction you get, because maybe you spend as much time in preschool, but you go to a higher quality preschool, right? You know, without the voucher, you would only go to an inexpensive preschool where there wasn't a lot of academic instruction. With the voucher, you go to just as much time in preschool, right? But you get a different quality of experience. So you could think of that as a sort of different mediator. Time. Well, obviously, we could make this have lots of pathways, but let's keep it relatively simple for now. And I've put here these parameters. So gamma 1 and gamma 2 are the person-specific effects of getting the voucher offer on these two things. So this if I'm an individual person, which I am, the voucher offers might affect how many, say I go to 5 more hours of preschool if I get the voucher. So my gamma 1 is 5 hours, whatever. Yours might be 10 or 0, right? If you're a defier, it might be -5 for some reason, right? It might be -5 because I might use it to buy a much higher quality preschool, but actually get less time in it, right? So it's not unreasonable that some of these could go, that the monotonicity assumption is not met either. And then this would be, the effect of the voucher offer on the quality of instruction I get. However we measure it, you could imagine that would vary across people too, depending on what choice they're induced to make differently based on whether they get the voucher or not. And then we've got these 2 delta parameters. These are the person-specific effects of those mediators on whatever my outcome is. So this delta 1 is the effect of every additional hour of preschool on my outcome, and delta 2 is the effect of whatever a unit of instruction on my outcome, whatever those are. The point here is that these are person-specific and they might vary across people. We're not making any assumptions about the distribution of them or whether they're all positive or all negative or anything like that. And obviously, if I could just make that picture have more mediators and more gammas and deltas, it wouldn't dramatically change things. And so if we want to estimate, if we want to get estimates of not these person-specific parameters, but the averages of them in the population, that's sort of our goal. We want to know what's the average delta 1, what's the average delta 2 in the population. How much does time in preschool affect my outcome on average? So how can we do that? Well, suppose we conduct an experiment in a lot of sites. In each site, we can estimate the average effect of the voucher on school readiness. So that's the intent to treat effect. That's nothing about the mediators, just randomization, outcome, simple experiment in every site. We get an estimate of what I'll call beta S, where beta S is the average of the person-specific beta. So everyone has their own beta. That is, there's a person-specific effect of the voucher offer on my kid's school readiness. And beta S will be the average of those across sites. And then in every site, we can also get an estimate of the gammas because of randomization. So we can say what's the effect of randomization to the voucher on hours in preschool, or what's the effect of the randomization on quality of instruction within a site on average. And so we get these gamma S's. So gamma 1S will be the average of the gamma 1s, and gamma 2S will be the average of the gamma 2s. Those are easy to get because we have randomization in every site. Nice unbiased estimates under very minimal assumptions, SUTFA basically, right? And then we're going to do this. And so first I'm just going to intuitively tell you what this is. We're going to basically regress the betas on the gammas. That is, we're going to say, what's the association between the intent to treat effect and these sort of first stage effects in a kind of regression model? Is it true that, holding constant the size of the effect on hours in preschool, that in sites where you had a bigger average effect on quality of instruction, you had a bigger average treatment effect? If you did, then delta is going to be a positive number, delta 2 will be a positive number, and that'll suggest that, boosting the amount of quality of instruction kids get boosts their school readiness, and so then quality of instruction has some effect on school readiness, and delta 2 is going to tell us how much that effect is. Chris? The gammas are the variables. The gammas are the variables. The deltas are the parameters. So it's a little bit weird, right? It's a regression model, but the things in the regressions, the betas and the gammas, are the effects of randomization on either the outcome or the mediators. They're not variables in the sense that we usually do a regression. They're site-specific effects that we estimated due to randomization. And then we get these coefficients here that are going to be under a set of assumptions that I'll talk about. Those are going to be estimates of the average effect of each of the mediators on the outcome. And you'll notice one other thing about this regression model. What do you notice about this regression model that's slightly unusual? There's no intercept, yeah. So any intuition about why there's no intercept? Think about it. We'll come back to it. But the key there is no intercept. All right, so delta 1 is the average difference in beta between two sites that differ in 1 unit in gamma 1, conditional on gamma 2 being constant and vice versa. So that's the kind of overview of how the model works. Now I'm going to talk about in more detail the logic of it. But first, let me give you a couple examples of this. So one is a paper by Greg Duncan, Pam Morris, and Rodriguez. They take 16 different random assignment welfare to work experiments, which are many of the same ones you were talking about earlier. And each of these programs had slightly different designs, and they were intended to affect a few different things. So some were really targeted to increase families' income. Some was intended to get people working more. Some was intended to reduce people's welfare receipt. Though obviously they all might have affected all three of those because those things are sort of related. And they also had measures of child outcomes. And so they were interested in the effect, not of the welfare to work program on kid outcomes, but they were interested in the effect of income on kid outcomes. If you raise a family's income, does that benefit the child? Well, they didn't randomly assign people to get levels of income, so they couldn't just regress kids' outcomes on income because they don't have random assignment. But they have some exogenously induced variation in income because people who are randomly assigned to these welfare to work programs, the people in the treatment group, in some cases, got higher income than the people in the control group as a result of random assignment. And so that part of their income is exogenous. And so they want to kind of use that part of their income. But the problem is that the welfare to work programs also affect these other things, the hours that people worked and welfare receipt, both of which also might affect kids' outcomes. So they want to identify the effect of one mediator of the welfare to work programs, that is income, but they need to take into account the fact that there are other mediators. So if you just had one site, you couldn't do this because you have one instrument, random assignment, but three potential mediators, your model's under-identified, right? Steve?
You might have said this, the impact on what outcome?
Some child measure of achievement, child achievement, or I can't even remember now. Do you remember, Howard? Yeah. Woodcock-Johnson, I'm sure, right? That's what it always is. But they have this done in 16 sites. They don't just have one site, they have 16 sites. And so they really have 16 instruments, right? Because they have randomization in each site separately. And so 16 instruments is enough to let them estimate the effect of three mediators. Another example is this MTO paper I mentioned. So in 5 cities, MTO randomly assigns low-income families to get to one of 3 treatment conditions. Either they get a housing voucher that they can use only to move to a low-income neighborhood. They get a regular housing voucher, which can be used to move to any neighborhood where they can find housing, or no voucher at all. So you have sort of 2 instruments in every site. And they have it in 10 sites, so they have 5 sites, so they have 10 instruments. And they want to know what's the effect of living in of moving to a low income, moving to a low poverty neighborhood. But they want to take into account other possible ways that getting the voucher might have benefited people, and so they really have sort of 2 mediators, and so they use this kind of a strategy. There's some papers you can look at later. So let me talk through the logic of the model. Does that make sense so far, what we're doing? We're trying to basically estimate the effects of multiple mediators when we only have really one randomization within a site. So imagine we have this experiment in lots of sites. Here's one site. Here's the kind of picture I just showed you. So the gammas are these person-specific effects of the treatment on the mediators. I'll call them M1 and M2. And the deltas are these person-specific effects of the mediators on the outcome. And if we wanted to write down what's the person-specific effect of the treatment on the outcome, that is what's beta, well, it's going to be gamma 1. Gamma 1, it's how much my treatment changes my mediator times how much a unit change in my mediator changes my outcome. So this is the effect of that top pathway. And then we have the same thing down here. And so the person-specific effect beta, how much the treatment assignment affects my outcome or my kid's outcome, is delta 1 gamma 1 plus delta 2 gamma 2. Does that make sense, Josh?
So we're still making an exclusion restriction.
So there's no, yes, so the exclusion restriction here is there is no direct pathway or no other pathway that I haven't shown here that goes from T to Y. That these are the only pathways there are, right? So it's not saying there's only one pathway, which you might say if there's only one instrument, but that we've listed all possible pathways. Well, if we knew a lot, if we had a good theory about how things work, I mean, you know, every time people use instrumental variables, they're comfortable saying they've listed all pathways because they list one and they're happy with that one, right? So I'm going to show you later on a method of doing this where we relax the exclusion restriction and we let ourselves not have an exhaustive list of all of it. But for now, let's imagine that we have a persuasively exhaustive list of all possible pathways. And moreover, we've measured them. Like we have to measure M1 and M2. It's not enough just to write them down, right? We have to actually, we're going to have to, if we want to estimate the effect of T on M2, we need to have measured M2, right? So. What's that? Well, the no intercept is that there's no other pathway, right? If there were another pathway, we'd have to stick something in here, and then it would look like an intercept because it wouldn't have an M associated with it, right? So that will become relevant later on, but that's the logic of it, yeah. So actually, this seems simple that we could just write down beta as this, but there's actually 5 assumptions that we just had to make right off the bat, even to write this thing down. So that might distress you a little bit. So the assumptions there, so one is SUTFA, which is sort of the stable unit treatment value assumption, which you've all heard about somewhere in 255 or elsewhere, I'm sure. And kind of without SUTFA, we can't make very much traction on this kind of a problem because the causal effects aren't very well defined. But the other assumptions are worth spelling out. So the second assumption is that the mediator M is linear in T within a person. So I didn't write the within a person, but that says that we can write down the person-specific effect of T on M as one parameter. That is, any unit change in T gets us an equal change in M. Now, if T is binary, that's sort of met simply because there's only one kind of unit change you can ever make in T if it's binary. But if T is a continuous variable, if we were randomly assigning people to vouchers of different amounts, right? You might get 1,000, 2,000, 3. Then we'd be sort of saying every $1,000 extra of the voucher has to result in the same amount of change in the mediator within a person. It doesn't have to be the same amount across persons, but it means for you, if I gave you an extra $1,000, no matter how much, whether that was the difference between 0 and 1,000 or 5,000 and 6,000, it would always result in the same amount of increase in your mediator value. So it's a person-specific linearity. So we have to assume that for this to work. We also have to assume the same thing for the deltas, that they're linear in Y within, or that Y is linear in M within persons. So every unit increase in your mediator value changes your outcome by exactly the same amount. There's a within-person linear association. If the mediator is binary, this is met, again, trivially because there's only one unit change you can make. But if the mediator is continuous, this, you could imagine it's not. So in order to write that little equation, we have to make those 2 assumptions. We also have to make two other assumptions. One, which you pointed out, the exclusion restriction, right? So there's no other pathway I didn't draw. If there were another pathway, I'd have to put in something for it. And then the other one is that the mediators act in parallel. That is, you see that T affects the M's and the M's affect the Y's, but the M's don't affect each other. There's no arrows connecting M1 to M2 or M2 to M1. If there were, then you'd have to add some extra terms in here because, now there'd be some effect that would go from T to M1 to M2 to Y, and we'd have to get that represented in here. So there's 5 assumptions that we need just to write down that kind of person-specific beta as a function of the deltas and the gammas. And now suppose we want to say what's the average value of this beta within a site T. So we want beta within a given site. Well, there should be a subscript S on all this, I guess, but there isn't yet. There will be next slide, I think. So the expected value of beta within a site is going to be the expected value of this thing, which is going to be the products of the expected values plus some covariance terms. And so I'm going to call the average delta 1, the average person-specific delta 1 we'll call little delta 1, and the average person-specific gamma 1 we'll call little gamma 1, and so on. So the little Greek letters are the averages, and the big Greek letters are the person-specific ones. And you'll notice here there's these 2 covariance terms. It will be convenient, as the economists like to say, to assume those are 0. So what do these mean? So Steve talked a little bit about these. These say that there's no covariance within a person between the deltas and the gammas. That is, the people who have bigger gammas, the people for whom the treatment affects the mediator more, are not the people on average for whom the mediator affects the outcome more. And as Steve pointed out earlier, there's reasons to think that might not be the case, right? I might think, hey, preschool is going to be really beneficial for my kid. So I think my delta is big. And if I actually know, and if I'm right about that, right? If that induces me for every extra $1,000 of voucher I get to buy as much more preschool as I possibly can with that, right? Then I might have a big gamma. I'm very responsive to the random assignment. And I have a big delta. So we would have a positive correlation between my gamma and my delta. You can imagine it going the other way, right? You might be a person who if you think your delta is really big, you already bought a lot of preschool for your kid. And so getting a voucher for it doesn't actually change how much you buy. So you have a kind of a low gamma because your delta is high and you had already invested sort of as much as one could. You don't want your kid to go to preschool for like 60 hours a week or something, so you don't buy anymore, right? So you could imagine these covariances as positive or negative, but more generally you can imagine they're not 0. And so in order to get to this equation there, we're going to assume they're 0. We're not making, in this formulation of it, any assumption about no defiers, right? So there's a different way to formulate this where you say there's no defiers, and then you don't worry about these covariances. But if we want there to be the possibility that some people have negative gammas and other people have positive gammas, then by definition there's not monotonicity. There are defiers, and so you either have to have one or the other assumption. You need no defiers or you need no covariances, one way or the other. So I'm gonna write it out here as the no covariance assumption. So far we got 6 assumptions. Yeah. Yep. Y linear in M. It may not be plausible. I mean, so I think the trick is remember you're saying Y is linear in M within a person. So you can't check it by looking at, say, the relationship between Y and M in the observed sample, because that's a cross-person regression, right? You're sort of saying here's some people with a high Y, what's their M? Here's people with a low Y. That's a between-person thing. And so whether it's linear in the between-person data doesn't really tell us whether it would be linear within people, I think. So you need somehow to do this. Now, one way around this is to add a second mediator, which is the square of M1. So now, say, it might affect me in two ways. It might affect my time in preschool and my time squared. Or you might just do it in piecewise, like there's one mediator is, do you spend, 0 to 10 hours, and another is 10 to 20. And then each of those mediators can sort of have a different effect. And if they have a different effect, there's no more linearity in sort of M. So, but that's fine. But you have to sort of think of any nonlinearity you can solve by adding more mediators to the model. But say you added M and M squared, then you're just saying, well, I think my relationship between conditional on my M, the relationship between M squared and Y is linear, and conditional on M squared, the relationship between M and Y is linear. It's the same thing you do in any regression model when you put in, multiple functional form terms. You're writing it out as a linear function of higher order terms. So you could do that here if you have strong reason to think that these linearity assumptions are not valid, or if you want to test them, right? If you put in a squared term and the delta on it was 0, you would say, well, there's no sort of within person curvature of this function. So it may seem strong, but it's testable to a certain extent. But you need it at some point. How sensitive these things are to it, I don't really know, though. Chris?
So putting an M squared term violates the parallel assumptions, and so we mechanically related to them?
No, because the M doesn't affect M squared in the like once the T affects M squared and the T affects M. I don't think there's no extra effect of M on M squared once you've done that. I think. I don't know. I have to think it through. But my hunch is you could sort of. It probably doesn't violate it if you sort of have the functional form right, I think. But yeah, I don't know. I haven't given a ton of thought to like how sensitive these things are to violations of this within person linearity assumption.
Just a thought, because I was thinking about that. Two things. One, if it's a binary mediator,
Not a problem.
not a problem. So, like, if it's employing or not, which oftentimes these things play a major role. So that's one thing. The other thing is, unless gamma, if it's a continuous mediator, unless gamma is really large, unless you're really moving the mediator, unless treatment assignment is really moving the mediator, if you're looking over small intervals, so small changes of whatever that mediator value is, then things will tend to be more.
Yeah, and it sort of only has to be linear in the range of M's that are to which your M's are moved by the treatment. So, and if everyone's moved about the same amount, then this sort of doesn't matter but I think you're right. I mean, I think it's a good question because it's not entirely clear that why we should believe this sort of in general, right? But I think if we worked it out, maybe it's not so sensitive to these things in lots of practical situations. But I don't know. Be a good thing to work out. Is there another question? All right, so here we are. We have this equation that says beta is delta 1 gamma 1 plus delta 2 gamma 2, where we're talking about these site averages of the betas and the gammas in this case. Now suppose we do this in lots of sites, so not just in one site, but lots of sites. And now in every site, we have a beta sub s equals the delta 1s. There should be an s on that gamma 1 times gamma 1s plus delta 2s times gamma 2s. So that's just doing the same thing in every site. So we have an s on everything. And now what we're going to do is we're going to rearrange things a little bit so that instead of delta 1s, we want to make those a common parameter. So we're going to get a sort of average of the delta 1s's. We'll call that delta 1. and an average of the delta 2s's. We'll call that delta 2. And then we're going to, since we changed things there, we got to add a bunch of stuff to undo the stuff we changed, right? So we're adding in delta 1 gamma s, and then we're subtracting off delta 1 gamma s, and we're adding in delta 2 gamma s, and we're subtracting off delta 2 gamma s, so that it works out, right? Steve?
I just want to comment, I think everything up until this page was strictly deducing the theoretical model.
Yeah, in terms of how we think the program, how we think it works, and who chooses,
How we think the world works.
yeah,
It's all about
how people respond to T and how people's Y responds to M and all that.
And now, and all those assumptions were part of the theory of the model. And now I think this slide, you're starting to talk about, okay, let's go get some data. That's what you just said, right? Let's go to these sites, we're going to get some data. So now we're going to talk about how to analyze it. So is that right? We're beginning to work toward a...
Yeah, though there's still one more assumption that's kind of, I think you would think of as theoretical model. And that's going to come here in a second. So I'm still writing this out as like there's just a bunch of sites and these are real parameters, and I'm trying to describe the relationship of these things across sites. And when we write it out this way, now we have beta s, which varies across sites, is a linear function of the gamma 1s and the gamma 2s, right? Where there's just a delta 1. That doesn't vary across sites. So this is, the first part of that just looks like a regression model. It says the site average effect, site average intent to treat effect is just a linear function of the site average gammas, the site average compliances, plus this error term, which I'm just going to collect into omega s. But omega s is this stuff. And so this suggests maybe I can, estimate the deltas through regression, because that's what we do, right? This looks like a regression model. Beta is a function of the gammas plus some error term. So we're going to think about trying to estimate those red parameters, the deltas here, through regression. And in order to do that, think about if we're going to do this by OLS, what assumptions do we have to make in OLS in order to get unbiased estimates of the deltas?
So delta 1 and delta 2 can't be correlated with omega s.
Not delta 1 and delta 2. Delta 1 and delta 2 are parameters. You mean
Gamma 1.
gamma 1, gamma 2.
But they're in omega s.
So the error term has to be independent, conditional on the, has to be independent of the gammas, right?
But aren't they in the error?
Yes, the gammas are in the error term, but that's not really the problem. The problem is that the deltas are in the error term. The delta s's are in the error term. So it turns out in order to fit this model and get an unbiased estimate, we need to assume this thing here. That is that the deltas and the gammas have to be uncorrelated. That ensures that the error term is independent of the gammas. So, because this is what we need. We need the expected value of the error conditional on the things in the model to be 0, right? So conditional on the gammas, that means those expected values of the deltas have to be 0, so that means the deltas have to be uncorrelated with the gammas. So yeah, so you're right. That the key assumption in OLS is we don't have error terms correlated with it, and so what that means in this case is the site-specific deltas aren't correlated with the site-specific gammas. So what would it mean for the site-specific deltas to be correlated with the site-specific gammas? Anyway, like think of a story. Think of this preschool voucher thing of a delta and a gamma. Josh?
Like, so in my local area, a voucher goes further for getting, better preschool situation. So I'm more likely to use that voucher. It's that simple.
Well, so that would say that the gammas might vary across sites, right? Because maybe the cost of preschool is cheaper in some places than others, so $5,000 might affect the amount of preschool my kid gets a lot more in site. But that's not a problem here. I didn't say that the gammas can't vary across sites. I said they can't covary with the deltas. So continue the line of thought.
So that's also a place where the value of the preschool that you're purchasing goes further for your outcome.
Or goes less far, right? The places that were more or less expensive. Yeah. I mean, suppose the cost of preschool is a good indicator of quality. And then the places where it costs a lot, you probably, your gamma is less, right? Because you can buy less, fewer additional hours of preschool with the voucher, right? But each hour might sort of matter more in such places because the quality is higher. So that's a story where the gammas and the deltas are negatively correlated. Places where you can buy a lot of extra hours if you get the voucher, are places where the effect of every extra hour is smaller. So that would be the kind of thing you might worry about, where you have a covariance between the gammas and the deltas that's going to mean that your estimates from this model won't be the average deltas. So there'll be some biased estimate. The other two assumptions you need here, one is you need ignorable assignment of the treatment within sites. Why do we need that? Because we need to be able to get unbiased estimates of the betas and the gammas to start with in the regression model, right? So how do we get that? Well, we have random assignment or ignorable assignment. So we need a design that has ignorable assignment within each site. And then number 8 is a fancy way of saying we need at least as many sites as we have mediators, right? So if there's only 2 sites, but we had 3 gammas, you'd have a regression model with 2 observations and 3 variables. Well, we know that doesn't work really well. Right? So you need at least as many sites as you have mediators so that there's at least as many observations in your regression model as there are coefficients to estimate. So this is a fancy matrix algebra way of saying.
The rank.
Yeah.
Right. But there's also a linear independent.
Yeah. So they have to be linearly independent in the sense that if the every place that moves gamma 1 by 1 unit moves gamma 2 by 2 units, then there's no separability between those 2 things, and you can't separately identify the deltas, right? So so this kind of gets both of those. Yeah, thanks for reminding me of that. So it gets you both of those features. So these are sort of assumptions about the design, the going and getting data in the world, right? You need data in the world that meets these conditions. But I think of this as sort of a theory thing, in the sense of the first 6 were theory. You need to think that the world operates in a way that the gammas aren't correlated with the deltas. There is a way to test this assumption, and Howard and Fatih and Page do, and I wrote a paper about it, which is, it might be in this. It's on the website on that reference list. I'm not going to go into that today, but there is a way to test this. It's not a super powerful test, but it's something, and a way to correct for it. So we describe a way to test for violations of this, and then to correct the estimates if this is violated. So let me just recap. We have 9 assumptions here. So it's worth looking at them all at once to remind yourself that this is not, as Steve was saying, it's simple when you just have random assignment, right? You just have, what do you assume? SUTVA and random assignment, right? So we have those, but we have 7 other assumptions, right? So this is so it should give you some pause. So I want to, speaking of pause, I want to pause here. We'll go back to our little poll. And the next question here is, I want you to rank these. I don't really know what most. So there's 9 assumptions. Rank them in the order you understand them the best. So 1 is the one you understand the best, and 9 is the one you understand the least. This is my way of trying to figure out how clearly I'm conveying these things. So you will humor me. You will help me out if you humor me on this. So 1 is the one you understand the best, I think. I don't know if that's... What's that? Oh, you can't do this on a phone, I guess. I guess you have to do this on... Yeah. This is anonymous, guys. We don't want to call anyone out. I don't even know how it's going to show us. How's it going to show us the rankings? This will be interesting. I see nothing yet. I guess you guys haven't done it. Yeah, I'm curious. Do you want to do this on my computer, Howard? I'm curious to see how this works.
Oh yeah, you can if you just go to Google on your phone.
I don't know. You're trying to rank them.
The URL.
You move around?
I don't know. How do you move? How do you do it? Do you have to? Oh, you drag them. I see. So like, grab one of them. Grab one of them and kind of drag it up or down.
Okay.
I don't know. Maybe 9 is a lot to rank, but I know. I should have said it the other way around. Start at the bottom. Put the ones you don't understand at the bottom. Because that's equivalent, right? Oh, look, numbers. Somebody ranked 3 of them 3rd. Or maybe that's the ties. Ooh, it's moving. Look at that. It's very satisfying. That's kind of cool. People understand random assignment. That's good. Yeah. Sutpha. So the ones they hear a lot, they understand. It's oddly satisfying. That one does not have sufficient rank. Mm-hmm. Mm-hmm. Because you spent a while on it this morning. That was number, but you were doing this the with insight one, right?
I did within and between.
Oh yeah, I guess you did, yeah.
Actually, in one of our groups, we really worked on it in one group. We actually did.
But also, this is like a relative ranking, right?
Yeah.
So
Right. Doesn't mean people don't know yet. But that is very cool.
Is anyone still sorting?
Is
One is most,
problematic?
no, clearest understood. Have you been doing them in backwards order?
No. Least plausible.
Start at the bottom. It's not about plausibility. It's about how well you understand the assumptions.
Howard, you're not allowed to vote. You understand.
Yeah.
It was about plausibility. Taking a poll on plausibility.
No, I was taking a poll on understanding. Possibly. Is anyone still doing this? Yes. Okay. All right. So you got these. So least well understood, sufficient rank. Does anyone want to try to explain sufficient rank? Who did understand it? Who didn't explain it ninth, or rank it ninth? Yeah. Chris.
it's just like I just see it as just like
Mhm.
each IV, so use as many sites as you want for each.
As long as the gammas are independent.
Right.
Yeah. If they're perfectly, if two of the gammas are perfectly correlated, you can't separate the deltas.
Or one gamma's perfectly explained. If you had a bunch of gammas, one gamma's perfectly explained by the other six.
Right.
It's like
Yeah.
a linear figures.
Yeah. But you can have one gamma that's constant. You're allowed to have one.
Without the intercept.
Yeah, because it's like having an intercept in the model, right? Normally you couldn't, right? You couldn't have a constant variable, but since you don't have an intercept, you could.
So one insight we have as we talk about this is the multivariate version of being able to divide by gamma when you have one extreme.
Exactly, yeah.
The one gamma can't be 0. And so when you do regression, you're dividing, you're inverting a sum squared problem. So
Right. You need to be able to invert the matrix, basically, right? And that's what this implies. Right.
But then if you had a fixed gamma, you couldn't then relax the exclusion restrictions.
Right. Right.
well, another thing is, of course, if one of them were all zeros, that would, if there was a gamma in there where, if in every site there was a gamma that was 0,
Um,
That would kill that.
that would kill that mediator.
well,
Not all.
it would kill the matrix unless you got rid of it.
Yeah, I guess that's right. Yeah. You'd have to get rid of an all zero row. Yeah. Right.
So if you're using a package, it would probably automatically drop it out.
So I'm gonna move on, but so the next least well understood one is the cross-site mediator compliance effect independence, and I have some examples of that. I want to come back to that one. And those were distant, I think. Does anyone have questions about the other ones? Lindsay?
Can you just talk about parallel mediators since we're just talking about the linearity and the gamma?
Yeah, so the parallel mediators say that a change in one mediator doesn't affect another mediator. And I'll show you.
But is that an assumption because when you wrote it, I mean, we could relax that.
Yes, you could. And I think I have an example where we can think about how to relax that. So the way I wrote it, yes, but if you draw an arrow, you can write it out. It requires some assumptions about the correlations of that path with other stuff needing to be 0. So you can add other paths up to some limit. Everything can't affect everything, but you can add non-parallel mediator paths, and then subject to some additional assumptions about the covariances of those paths with other paths, you're okay.
Case in point, Duncan and company, what is that?
Yes, I'm going to come to that one. Right? So theirs is sort of clearly non-parallel. So let's go back here. All right. So these are the three big ones that are sort of specific to this enterprise, really. The parallel mediators, the cross-mediator compliance effect independence, and the exclusion restriction isn't specific to this, but it's sort of deeply necessary for what we're doing here until we relax it. But right now it is. So here's some examples of the assumptions. So here's the Duncan, Morris, Rodriguez paper. Remember, there's assignment to welfare work programs. There's 3 mediators: hours worked, income, and welfare receipt, and then some measure of student achievement. And it's quite reasonable to imagine that the hours worked might affect income, right? Unless every hour you worked, your wage went down, so that would be a kind of sad thing.
Or you were a salaried employee.
Right. Yes, a professor, for example. And welfare receipt also would affect income. That is, if you go off welfare receipt, you lose income, right? So there's clearly violations of the parallel mediator assumption here. And we can relax it. We can let there be these lambda terms that go from one mediator to another and write out the beta as a function of gammas, deltas, and lambdas. And if you went through the sort of same exercise of taking expected values, and you'd get some covariances in there, and you'd then have to assume those covariances were 0 in order for it to turn into something that looks like a regression model. But you can put them in. You just need these extra assumptions, essentially, right?
So do you need more instruments to deal with that situation? Those two arrows weren't there, those two lambdas?
Yeah, because you're trying to estimate more parameters now. You're trying to estimate lambda parameters as well. What's that?
Some of those downstream ones are acting like instruments for some of the ones that are really.
Yeah, so you end up trying to estimate the 3 deltas, and the variables in the model are now become gammas times, they either are gammas by themselves or gammas times lambdas, I think. And so maybe you may not need more instruments depending how you set it up, I think. Yeah. So the idea is to think about the assumptions. If you really don't, like in this case, if you really don't buy the parallel mediator assumption, you need a more complicated model and then figure out what other assumptions you need and whether you buy those, right? The Klingleib and Katz MTO paper, their model is really this. You get a voucher offer, and that might affect whether you use the voucher. That is, whether you move to a low poverty neighborhood. And obviously, if you use it to use to a low poverty neighborhood, it probably affects the poverty of the neighborhood you live in. But they're concerned it may also affect your outcome in other ways, right? Other than just through the poverty of your neighborhood. It could be other characteristics of the neighborhood, or other ways that using the voucher benefited you. Other ways that just mobility per se benefits you, say, even if you didn't move to a lower poverty neighborhood, right? So their model is like this. There's really not a gamma 2, because in the model, there's really no way that being offered the voucher can affect your neighborhood poverty if you don't actually use the voucher. And so there's really just a gamma 1, but then there's a sort of non-parallel mediator. So they don't do it this way. They sort of act like there's 2 mediators and they're parallel. But I think if you thought about the model, you would want to write it out slightly differently and have beta would be, gamma 1 times delta 1 plus gamma 1 times lambda 1, 2 times delta 2. You'd have 2 terms, but the second term would have this lambda delta thing in it instead of just a lambda. But it would still work out. You can still make the model work. You just have to think a little bit differently about it.
John, one way to think about that too is that you're kind of decomposing what used to be the local average treatment effect or the positive average multiplier effect, because other people who did this originally just said the voucher offer affects voucher use, that affects the outcome.
Right.
So the effect of voucher use on the outcome was the local average treatment effect, and now that's being partitioned.
Right.
That's being modeled as an indirect effect.
Yeah, so it's sort of like they were doing an ITT of voucher use on this kind of almost, and now we're saying let's break it up into a mediated pathway and a sort of direct pathway. So like from here on down, there's sort of not an exclusion restriction, right? Because there's a mediator and then something else. And so that should give you some hint that we can draw a something else pathway that essentially is a relaxation of the exclusion restriction. And then let's think about the compliance effect independence assumption. So again, this is Duncan. I've taken out the little arrows there because they're not relevant to this particular point, but not to say they don't belong there. But the compliance effect assumption says, and I've got these written as the site average thing, says that every one of the gammas is independent of every one of the deltas. So we need to think about what kind of sources of variation there would be in gammas. Why might gamma vary? Why might delta vary? And are the reasons that they vary related to each other? That's one reason why you might have a compliance effect independence violation, right? So for example, suppose that labor markets with low wages, you know, your income is not much affected by the treatment because there aren't many high-paying jobs to get, right? So you don't get as much of a boost from having the extra skills you get. But it might also be that things are a lot cheaper in those labor markets, and so every extra dollar of income buys you more that's beneficial to your kid, right? So in that case, like gamma 2s might be sort of lower than average in those sorts of sites, but delta 2s might be higher than average, right? So you get a kind of a negative covariance there. So you can sort of imagine stories like that get you some covariance that you might want to worry about. So I think it's useful just to think in general why the gammas might vary across sites, and it's useful to go back to the paper that Mike Weiss was talking about yesterday, that Mike and Howard, who else is on that paper? Tom Brock, right? What?
Oh,
that one, yeah, right? About sort of why might there be heterogeneity in effects across sites. So the gammas are just effects, right? They're effects of random assignment on the mediators. So why might they vary? So in that paper, they talk about 3 things that start with C, none of which I remember right now. Composition, contrast, and context. Context, clients, and contrast, right? C, anyway. So, you know, the contrast one way of thinking about the contrast is there might be different treatment implementation in different places. Either by design, like welfare to work, the programs were actually designed to work differently in different places, right? So there was really a different treatment condition. Or just because some places have lower capacity to actually implement a program well than others. And the other part of the contrast might be that there's different control conditions, so the counterfactuals of what people get in the absence of the treatment might vary across sites. So for the same reasons that intent to treat effects might vary, you know, effects on compliance might vary. And there might be different populations. Some places might have, and by compliant people here, I don't mean, you know, just pushovers, right? But people who are predisposed to respond well, that is, to respond a lot to whatever the randomization is, like people who really will take up the preschool if they're offered a voucher, or who will move if offered the housing voucher or something like that, right? So people who are compliant with the particular instrument. So the populations might vary across places. Or there might be contextual differences that affect it. So local labor market conditions, entry-level wages might affect, for example, what effect the welfare to work programs have on employment, right? So similar stories as Mike was talking about yesterday. Why might the deltas vary across sites? Well, again, for a variety of reasons. One is that the mediators might sort of be implemented differently in different sites. So if you thought going to Head Start was a mediator, well, each Head Start center might vary in some ways, right? And so some may be more or less effective at promoting whatever your outcome is. Again, different populations and different contextual conditions like cost of living, you know, effective income will depend on local cost of living things, right? You all know that, living in the Bay Area, right? And then why might the gammas and the deltas not be independent? And, you know, just a couple kind of things. One is because of this kind of selection on expected effects. This is the sort of thing we talked a little bit about earlier. So sites where people believe the mediators are effective might be sites where people comply a lot, you know, get a lot of the mediator in response to the treatment. Or common contextual conditions that might affect both. So this is like the story about cost of living and wages, or cost of preschool and quality of preschool, those kinds of things, right? Or again, populations might differ across sites that lead to kind of common or correlated effects of the gammas and deltas. So the point is here, there's a little bit of a trick here is you want the gammas to vary a lot across sites, right? It's a regression model. The more variation there is in your x's, the more easily you can estimate the coefficients, right? So you want You want delta to vary. I mean, you want gammas to vary a lot. But you don't want them to vary in a way that's correlated with the betas, right? So you want that covariance to be small, but you want them to vary a lot. And if you think about it hard, you can often worry yourself into paralysis here, I think, right? So that leads to this sort of set of concerns is, these models rely on a lot of assumptions, 9 to be exact. And some of them are often not particularly plausible. The exclusion restriction, the parallel mediators assumption, the between site independence of the compliance and effects. So, you need to have good theory or something to justify them. And you can't just sort of say, well, I have a multi-site trial, therefore this will work, right? You need some other evidence to lean on here. And the other concern about these is you may need lots of sites. Like a regression model with 6 observations is not a very powerful regression model unless it's really super linear, right? So in order to get good, relatively precise estimates of the delta, even if all the assumptions are met, you may need a relatively large number of sites. So you need multi-site trials that have a good number of sites,
Can I ask you?
Yeah.
I meant to ask this earlier. So, Klinkatz and Lieber,
Yeah.
they got 5 sites and 2 mediators. So 5 sites and 2 independent.
They have 10. They have 2 instruments per site, so they really have 10 instruments. But so think of it as 10 sites, sort of. But yeah,
Were they different treatment conditions?
there's 3 treatment conditions in each site, so they randomize, into 3 conditions. So, but still, it's 10 sites, 2 mediators. Not the most high-powered regression.
I'm starting to think about leak instruments that we want, again, first of all, if we're using each site as an instrument and if the site happens, the compliance happens to be particularly low, how does that become problematic? Or even if we're thinking about the deltas for each of the mediators, are we assuming a certain strength in choosing a mediator?
Yeah, great question. So I'm going to get to that in a little bit, but there is, as I say here, or no, I didn't say here, but there's a finite sample bias worries, and they don't arise for exactly the same reason they do in a single instrument model. But even if all these assumptions are perfectly met, there's, like any IV model, there's some finite sample bias, and so we'll talk about how big that is and when you should worry about it. So we have a lot of assumptions. The good news is the bias due to the compliance effect non-independence is often not large unless the covariances are really quite big, and it's testable and detectable if it's really large, and can be corrected. So we have this paper that tries to deal with that piece of the problem. And then the exclusion restriction, as we'll show, we can relax it or test it to see if we believe it. And parallel mediator assumptions, we can add more terms to the model, and so that can be sort of somewhat relaxed too. So these aren't damning, but you should approach this kind of method, I think, with some substantial trepidation.
On that last one that you could test it, that's kind of a novel idea.
Yeah, and you test it because the model's over-identified, essentially, right? You can never test the exclusion restriction when you just have one instrument and one mediator. If all the other assumptions are met, then you can test the exclusion restriction.
By that you mean since you have so many mediator instruments, and if you have a lot of sites relative to a relatively finite number of mediators, so that gives them leverage for that last one.
Yeah, so I'll show you how to do that. We're gonna do a little exercise, and then I'm gonna come back and do that stuff. So let me just show you some pictures. So let's imagine there's just one mediator because it makes it easier for me to make pictures. So then the model is just the beta S, the intent to treat, is delta times gamma S plus some error term.
That's the one I had as well.
That's the one you have, exactly. That's the one you have this that you estimate as option 3 or option 2 this morning, I think, right? And
also that two-stage, that is equivalent to two-stage.
it is if it's weighted the right way, yeah. So this error term, remember, is delta S minus delta. It's sort of deviation of the delta S from the average delta times gamma. And so the error depends on gamma, so the error is sort of heteroscedastic, right? It's going to, if delta has sort of a common variance across the sample, then the error is going to tend to get bigger as gamma gets bigger. So you have a sort of heteroscedastic variance. So you might have data that look like this. This is just made up data. But if these are your gammas and these are your betas, you're just regressing beta on gamma. And there's no intercept, so it sort of has to, so your regression line is sort of nailed to the origin, right? And then you're fitting it through these points. And because delta, if you, let me do this. So like here's our average delta, that's the slope. But if you tried to estimate delta in any one site, which you could do in this case because you only have one mediator, the delta S here, this is a place with a low delta S, right? So, you get a lot of gamma, big gamma, but relatively small beta because delta's small. And, here's a place with a big delta S, big beta, moderate gamma, but delta is big, so you get the big beta, right? So you can sort of think of the regression line you're fitting there as the average of those delta S's. And it's going to be identified as the average as long as these gammas and deltas don't covary. If they covary, these dots are no longer going to fall along a straight line, essentially, right? Suppose that as gamma gets bigger, delta gets bigger, then this is going to end up being quadratic, sort of. It's going to sort of go up because the big gammas are going to have the big deltas, and you're going to have all your points way up there. And the small gammas are going to have the small deltas, and you're going to have the points down here. And so you'll end up with sort of a curved line. And that's essentially the intuition behind the test of whether or not that covariance assumption is met. If this regression line has curvature to it, that says that the deltas and gammas are correlated with each other. But so essentially what we're doing is we're just fitting in this regression line, and we're nailing it to the origin. And we're doing it in a multivariate sense if we have multiple mediators, not just a univariate sense like this. So let me say a thing about finite sample bias, Chris. So, this is the thing we want to estimate. We want to regress the true betas on the true gammas. That would give us the answer we want. But we don't observe the true betas and true gammas. We only get estimates of them from finite samples, so they have error in them. And it's fine if you have error in the left-hand side of your regression model, right? That doesn't really hurt anything. But error in your covariates, what does that usually do to your regression estimates? I heard a word. Attenuates, yeah. So it usually will bias delta towards 0, right? Because there's measurement error in the x. It's not going to happen the same way here. The reason it biases in a regular regression model, we think of the error in beta as uncorrelated with the error in gamma. And so when you work it out, that means delta is going to get biased towards 0. But what we have here is beta S gets estimated from the same sample as gamma S. That is, within a site, we had to estimate the effect of the treatment on the mediator, and we had to affect the treatment on the outcome, but it's the same exact people in the site, right? And suppose that in some site, when we randomly assign people to treatment, we get a few more people in the treatment condition who just would have had higher values of the mediator anyway, right? Just by random chance in this particular sample. Well, if there's selection bias, that is, the people who have high M's would have high Y's anyway, right? That's why we don't want to just regress M on Y on M. Then anytime we draw a sample that has people with higher than expected M's in the treatment group and lower than expected M's in the control group, We're also going to tend to draw samples that have people with higher than expected Ys in the treatment group and lower than expected Ys in the control group if there's selection on M in relation, like if the people who choose M are also the ones who have high values of Y. And so the error in beta will be correlated with the error in gamma, because we're going to estimate the effect of the treatment on M from the exact same sample as we estimated on treatment effect on the instrument effect on Y. And so these two errors get correlated with each other, and that means delta is biased, but it's not necessarily biased towards 0. It's biased towards the OLS bias. That is, if you just regressed Y on M, which you wouldn't want to do because M isn't randomly assigned. But if you regress Y on M, you get some coefficient, and you're worried that that has some selection bias in it. This delta will be biased in the direction of that selection bias, right? So, so this is the version of finite sample you get here is due to the fact that we have error in the gamma, and it will be in the direction of biasing the IV estimate towards what OLS would have given you, which is the same thing finite sample bias does when you just have a regular old IV model. But the question is, how big is this finite sample bias? Is it worse than you get with a regular IV model? Is it better? It turns out it's better, and I won't show you that. But there's less finite sample bias in this case than there is in the IV model with one instrument. The last thing I want to say about this is the weighting. So remember, the model we fit is we regress the beta hats on the gamma hats, and then there's some error term. Now imagine that the deltas are constant across all sites. That is, every site delta S is exactly the same. Then this part of the error term just goes away because delta S minus delta, that's always 0, and this just disappears, right? And in that case, we just are going to really regressing the beta hats on the gamma hats, plus this part of the error term. This part of the error term is just the sampling error in the beta hat. And we know what the variance of that thing is. It's the square of the standard error, or that's a good estimate of it. And so if we assume that the deltas are constant, we can fit this regression model with weighted least squares where we know what the weights should be, right? And it turns out that's exactly what two-stage least squares does if you have instruments that are interactions of the treatment by the sites. So it's mathematically identical. If you have multiple mediators and you have site by treatment interactions and you estimate all these gammas, and then you have this regression model, the second stage model is the outcome regressed on the M hats from this, right? So this is two-stage least squares like you've all seen in class, I know. The deltas you get from this are identical to what you would get if you just regress the beta hats on the gamma hats with where you weight them by the inverse of the squared standard errors of the betas. It's just weighted least squares. So what does that tell you? That tells you that two-stage least squares is equivalent to assuming that the delta is constant, right? So two-stage least squares is making the assumption when you write down this model that the delta has no subscript S on it, right? It's just, there's just one delta per mediator. And so what that means is that two-stage least squares are going to give you the wrong standard errors if there's really heterogeneity in the deltas, because it's not taking into account the variability in the deltas. If there's homogeneity, then two-stage least squares gives you exactly the same answer and gives you the right standard error.
Just looking, so two-stage least squares with site fixed effects?
Yeah, so this is site fixed effects and site by treatment interactions. That is, there's a separate gamma in every site, site fixed effects, and then the M hats, right? So one way to think about this isn't doing something really different than two-stage least squares, sort of setting it up differently, and it's more flexible than two-stage least squares because you can relax exclusion restriction assumption or parallel mediator assumption or anything. Another way to think about this is two-stage least squares has this parallel mediator assumption built into it that you might not notice if you just wrote it out this way. It has all the assumptions written down as before, except it assumes delta's constant, so then it doesn't have to assume the independence of the deltas and the gammas, because if delta's constant, it can't covary with anything, right? So it's sort of, by making delta constant, it sort of simplifies the set of assumptions you have to make, but you have to wonder how much you believe that delta's the same everywhere, right? And then the last thing is, if we don't assume it's constant, now the error term has this thing in it and this thing in it. And so we can still do weighted least squares, but we weight by a precision weight. That is, we think the variance has some sort of variance that's really true variance between the betas, because, you know, like those scatter plots, you know, if the deltas vary, the dots don't all fall in the line. And then it has some sampling error in it. And so we can do this with precision weighting. You could do it in something like HLM or a meta-analytic regression or something like that. So this will give you better standard errors under the assumption that delta might be heterogeneous, right? Does that make sense? So I want to stop here and have you answer a few questions. So here's your next question. Under which assumption is two-stage least squares inappropriate for the multi-site, multi-mediator IV model? Your choices are A, B, C, or D. Percent of one person responding. Maybe more than one, who knows? Or a lot of people who agree.
When you say two-stage, yeah, you mean classic two-stage square?
Yeah. How can answers go away? Oh, you can change your answer? I don't.
Yeah, you should close the screen while people
Oh, am I supposed to? Yeah.
responding, although I guess they need to know what the categories are.
It should be on your thing. All right, I'm going away from it. Can't see. Of course, if I went back to the slide that had the answer on it, that wouldn't help either. All right, well, I think that's enough time. What do we got? 77% say the deltas vary across sites. 79. That is the correct answer. So two-stage least squares can have varying gammas. It can have correlated gammas. It can have more than one mediator. But it's not the right model if the deltas vary across sites. It assumes the delta is constant across sites. And you can see that if you look at the two-stage least squares model, it has one delta for each p here indexes mediators. There's one delta for each mediator. There's no subscript s on that, right? We're assuming there's just one thing. And the operative implications, the weights are different. So if you do it in this way, where you regress the betas on the gammas, you can weight it in a way that will get you the right standard errors and probably a less, I have to think about the bias, but maybe a less biased estimate too. I mean, if the assumptions are all correct, there's no bias other than finite sample bias, but it should give you the right standard errors. All right. Next question is, what questions do you have? So this is my way of, you can write that down as your question. So, So, or you can ask them out loud, but if you don't want to ask them out loud, you can write them down. And I'm going to hide the screen. Oded?
Do you have non-simulated data that you've tried to do this kind of work on?
Yes. So we did some real data with Tennessee Star and reading first in the one paper, and then I'm going to show you some simple results from some quasi-real data after the break.
It's like in Tennessee Star, what did you hypothesize were the multiple mediators?
I no longer remember. I think just class size. I think we did it with one mediator, and we were looking to see whether that. So your treatment was assignment to a small class. Mediator was the actual class size. So it's a continuous variable, and then we're looking to see whether or not. We're looking for estimates, but we also were trying to test that no covariance assumption to see whether the site-specific gammas were correlated with the site-specific deltas. And then I forget what we did reading first, and then we corrected it for any bias that came. I think we didn't find much evidence.
It was not a big correction.
Yeah.
So it didn't look like, and if you looked at the graph, it didn't look like there was a lot of curvature.
It looked like a little curvature, but not enough to amount to any substantial bias, I think. I forget what we did in reading first. It was time on those 5 dimensions or something. Remember, it was those instructional practices sort of a thing, yeah. Other questions, verbally or in writing? Lindsay?
So I'm thinking about the claim, the MTO
Mhm.
conceptual one that you have out there, and it makes sense to me that you would see an effect of the offer on use, and then maybe that goes, that's how neighborhood property is affected. But why isn't kind of this first little part that looks different more common in all of them? Like in your first example, like why isn't there like use of the voucher to go to pre-K? Why isn't that in there, which then affects your hours in pre-K?
You could do that, I think. I mean, in some ways, it's sort of, maybe you put a little mediator in here that's like, did the counselor tell you how to use the voucher kind of a thing? I mean, obviously, you have to have a theory of the program, how the program works, and then you want to make sure you have in your model, in this kind of a model, the key mechanisms that you're interested in sort of testing. And you might not want to test every single relationship. So you might not want to know, the sort of use the voucher. You don't really care about whether people use it. You sort of are interested, often we're interested from a sort of scientific point in these things, like what's the effect of extra income, or what's the effect of reading to your kid? But we can't randomize those things very well. So we have some experiments that induce exogenous variation in those things, and we want to use the experimentally induced variation in those things to estimate the effects of those things. So often we care about the deltas from a sort of scientific point of view. When we're thinking about program design, we often care about the gammas and the deltas because we want to know maybe it didn't affect people's neighborhood poverty because nobody actually used the voucher or something like that. And then we might be interested in the gammas or even other kinds of gammas, like did people get counseling about where to move, or did they try to apply to places but then they were just turned down all the time. So depending sort of what part of the theory of action of the program you're interested in, or whether you're mostly interested in these kind of deltas, you might structure the parts of the model you pay attention to differently. And as long as, if everything that gets you from here to here is just in a line, or just imagine that there's a bunch of mediators that get from voucher offer to voucher use, but none of them go anywhere else. None of them are errors going anywhere else. And so just think of them as a big package called gamma 1, and we don't really care about them. Call it gamma 1. But if you cared about them, you would want to specify them. So I think it's not that you have to write out the complete model of the universe with everything that ever happens in it. You have to write out a model that focuses on the parameters you want to estimate, and then has this sort of diagram that justifies, I have nothing going here, so I've made a sort of assumption that getting the offer doesn't affect you if you don't use it, which may be the case here, but you could think about the preschool case where the first mediator was like how much time you spent in preschool, and you could imagine that it affects you in other ways. You just get a windfall of money if kid was already in preschool, because you just took, you swapped out the money you were spending for the money they were giving you, kind of thing. So I think you gotta know which parameters you want to estimate, and then structure it in a way that has those parameters in it, but not any extraneous ones you aren't really interested in, but that has a defensible kind of causal pathway structure.